Good morning, dear ladies and gentlemen. Today, I am going to tell you about the study of the soliton dynamics in an oscillating magnetic field. Before I proceed to the scientific part of the talk, I want to express my sincere thanks to organizers of the conference for the possibility to share the results of my study with you. And my sincere thanks to Professor Juana Chila for his deep support of Ukraine, Ukrainians, and myself during 10 years of Russia's war against Ukraine, and especially during the last 2 years of the full-scale invasion. I dedicate this talk to 50 years of the Davidov soliton. The first paper has been published in 1973 by Davidov and Kislucha, and in which the soliton mechanism has been developed to explain the energy transfer in macromolecules on macroscopic distances. Later, this mechanism has been generalized to describe the charge transport in low-dimensional systems, and the class of these low-dimensional systems is very big. As you know, it includes not only macromolecules, but also conducting polymers, Wedgwood salts, low-dimensional superconductors, and many other systems. The dynamical properties of solitons are manifested in external fields. In particular, external fields modifying propagation of solitons along molecular chains can affect charge transport processes in general. Moreover, there are experimental evidences of biological impact of oscillating magnetic fields. Let me remind you that Davidov's soliton, or molecular soliton, sometimes is called, is a quasi-particle, electron-hole or molecular excitation, bound with the self-created deformational potential due to electron-lattice interaction. It can be compared with the polar. In fact, it is a polaron effect, and Davidov soliton is a kind of a large polaron, with the difference that in Davidov soliton, electron-lattice interaction is taken into account exactly without using the perturbation theory. The simplest model is based on the uniatomic molecular chain shown on this figure, where black dots are atoms or molecules which can be displaced from their equilibrium positions due to the presence of the external particle like an electron. The Hamiltonian of this system is the Fröhlich type Hamiltonian. It consists of the Hamiltonians of electron, phonons, and their interaction. And in the continuum approximation from this Hamiltonian, we can derive the system of two coupled equations, nonlinear equations, for the electron wave function psi in the deformational potential described by the molecular chain deformation rho, and the equation for the deformation itself, which is caused by the presence of the electron on a particular place of molecular chain at the given time t. In the adiabatic approximation, this system of two equations can be reduced to the nonlinear Schrödinger equation with the nonlinearity constant proportional to the square of the electron lattice coupling. And its solution is a well-known free soliton, the inverse hyperbolic cosine function, which in our case is normalized to 1 because psi describes the amplitude of the probability of electron. To study the effect of external magnetic field on solitons, we have to generalize our system to a three-dimensional model. So instead of the coordinate, one spatial coordinate x, we introduce the radius vector with 3 spatial coordinates. The wave function is also generalized to three-dimensional case, but because of the presence of electron-phonon interaction only along molecular chains, it can be represented as the product of two functions, one which depends on x and another in a transfer direction depending on two other spatial coordinates. And according to quantum mechanics, we have to substitute the momentum operator of the electron by the elongated momentum operator, where capital A is the vector potential of the magnetic field B. So in this case, our equation of motion can be represented as the time-dependent Schrödinger equation with the Hamiltonian H, which is this kinetic part with the elongated momentum operator and the deformational potential rho with the coupling constant sigma. Dynamics of the soliton in constant magnetic field has been studied many years before in the connection with application of soliton model to explain superconductivity of low-dimensional systems and high-temperature superconductivity. Now I am interested in the time-dependent magnetic fields, in particular harmonic magnetic field, as written in this equation. B of t equals B naught times cosine omega t. It is convenient in our model to study separately two cases of the field orientation: longitudinal, parallel to the chain orientation, and perpendicular to chain orientation. So in the longitudinal magnetic field, I will use index L, longitudinal. The magnetic field contains only, includes only one component, and it is convenient to choose the vector potential in this form. So the Hamiltonian, in the presence of such a magnetic field, is again can be represented as the sum of two terms. One, which is the soliton part, which is not affected by the magnetic field, and the part of the Hamiltonian in the transverse direction, which is the kinetic energy of electron in y and z direction, plus modification by the presence of the magnetic field with the given vector potential. For this Hamiltonian, the electron wave function can be represented as the product of the soliton wave function depending on x coordinate and the part of the wave function in the transverse direction depending on components y and z. According to this Hamiltonian, we can represent this component of the wave function in the transverse direction as the plane wave in one direction, for instance, y, and some unknown function in another direction, z, for which we obtain from the Hamiltonian the following equation, which, as we can see by its form, is the equation for the harmonic oscillator in the oscillating in time magnetic field, where value z0 is determined by the y component of the electron momentum and by the magnetic field. The solution of this equation is expressed via the Hermite polynomials Hn depending on the displaced argument z minus z0 multiplied by this exponent, where the value omega naught and the frequency of oscillations in the Hermite polynomials are given by this expression. So the omega naught is proportional to the magnetic field and inverse proportional to the cyclotron mass, where cyclotron mass is determined by the product of Y and Z components of the effective mass. Much more interesting is the dynamics of soliton in the perpendicular magnetic field, perpendicular to the chain direction of the molecular chain. So the vector potential has the component in the perpendicular direction, for instance, Y. The vector potential for this magnetic field can be chosen in this form. Again, our Hamiltonian can be represented as the sum of two terms, soliton part modified in the perpendicular magnetic field plus the part of the Hamiltonian which describes propagation of electron or dynamics of an electron in the transverse direction. This part is the Hamiltonian of a free electron in Y and Z direction, while the soliton part of the Hamiltonian includes part of the free soliton, kinetic plus deformational energy, plus the term which is determined by the magnetic field. So for this Hamiltonian, we represent the wave function as the product of the modified soliton wave function corresponding to this Hamiltonian and the part of the wave function in the transverse direction, which according to this Hamiltonian is the plane wave, normalized to 1. Equation for x component of the wave function is written here. In the left-hand side, I have put the terms which describe the free soliton, and in the right-hand side, there are terms which take into account the presence of the magnetic field. It is convenient to introduce the dimensionless parameters and variables, spatial coordinate x, and dimensionless time tau, dimensionless frequency omega capital, which is proportional to frequency of the magnetic field and inverse proportional to the nonlinearity constant. And in these variables, our equation takes the form written here. So again, in the right-hand side, I keep terms which come from the presence of the magnetic field, and in the left-hand side are the terms which describe the free soliton. The coefficient in the right-hand side term of the equation, epsilon, is proportional to the square of the magnetic field intensity and inverse proportional to the square of the nonlinearity constant G. It is easy to see that this coefficient is very small even for very large magnetic fields because of the presence of this electron charge and speed of light. Taking this into account, we can represent the chain deformation as the sum of two terms, where the first one comes from the pure soliton wave function, and the second term is modification of the deformation, which is connected with the change of the soliton wave function due to the presence of magnetic field, change of the parameters of the soliton dependence, their dependence on time, and so on. So, substituting this expression into the first equation for the wave function psi, we come to the modified nonlinear Schrödinger equation with the right-hand side with a small coefficient epsilon, where function capital R is given in this expression. So magnetic field and change of the deformational potential. This equation can be solved using the perturbation theory based on the inverse scattering technique developed by Karpman and Maslow many years ago. According to this theory, the solution of a soliton has parameters which change in time slowly. The wave function can be represented in this form. It depends on the running wave coordinate zeta and its phase phi. Using this form, we can calculate the correction of the chain deformation. It is proportional to the hyperbolic tangent, and it defines the perturbation term in the right-hand side of the modified nonlinear Schrödinger equation. Namely, this presence of this term results in the dependence of soliton parameters on time. Again, the wave function of the soliton, its parameters zeta and phase phi. For the parameters, we get the integral differential equations from the inverse scattering method, solving which we find the time-dependent parameters, in particular, soliton amplitude and also width, because width and amplitude are connected through the normalization condition. And it turns out that amplitude and width are constant. They don't change in time. Center mass coordinate is, as one could expect, proportional to time with the effective wave vector mu, which contains parts which are proportional to time and parts which oscillate in time with frequency of the capital omega. And phase, I don't waste the time on the long expression for phase. Here the constants C1, C2, C3, and C4 are constants of the integration, and there is also parameter alpha, which determines this effective momentum of the soliton. Alpha is written here. It depends on the velocity of the sound in the chain. So, in a magnetic field perpendicular to the molecular chain, electron propagates as a soliton whose parameters are oscillating in time functions with characteristic frequency omega, which is proportional to the frequency of the external field and inverse proportional to the nonlinearity parameter G. And thus, we come to the conclusions. Soliton dynamics in oscillating in time magnetic field depends on the orientation of the field, on its amplitude, frequency, and on the chain parameters. In particular, in the longitudinal magnetic field, electron propagates along the chain as a free soliton. In the perpendicular direction, it is described by the functions of the harmonic oscillator with the cyclotron frequency, which depends on the intensity and frequency of the magnetic field, while in a perpendicular magnetic field, electron propagates along the chain in a soliton state whose parameters oscillate in time with totally different characteristic frequency, which is proportional to the frequency of the magnetic field and inverse proportional to the nonlinearity coupling constant and exchange or resonance interaction in the chain. Such change of soliton dynamics in oscillating time magnetic fields affects charge transport processes in low-dimensional conducting materials. with intermediate values of the electron-lattice interaction, whose ground electron state corresponds to soliton. So these are polydiacetylene, platinum chains, Bechgard salts, and many others. Hence, magnetic field can significantly affect charge transport processes, generally speaking, in micro and nanoelectronic devices, in devices of biomimetic technologies based on polymers and other quasi-one-dimensional non-functional materials. In biological systems, external alternating magnetic fields change the dynamics of solitons in macromolecules, and thus these fields can affect charge and energy transport in the electron transport chains in the redox processes in mitochondria. And these results can explain the mechanism of the biological effects of external alternating magnetic fields and the mechanism of the therapeutic action of such fields. Thank you very much. Stand with Ukraine. I will be glad to answer your questions.